Hello everybody. In this video we are going to be taking a look at the solutions to the Honors Sound homework problems 16 through 20. Let's get started. Hannah places an open vertical glass tube into a container of water so that the lower end of the tube is submerged. She holds a vibrating tuning fork over the top of the tube while varying the water level in the tube. Hannah notices that the loudest sound is heard when the distance from the water to the top of the tube is 32.7 centimeters, and again when the distance is 98.2 centimeters. What is the frequency of the tuning fork? So we're given two lengths here, where the first length is 32.7 centimeters, which I have to convert to meters. So that's going to give me 0.327 meters. And this length represents the length that gives me my fundamental frequency or my first harmonic. The second length that I'm given at 98.2 centimeters, which again converting to meters will give me 0.982 meters. This length is going to give me the length at which my third harmonic occurs. And remember, this is a closed tube, so one end of the tube is submerged in water, so only one end of the tube is open to the air, which makes this a closed tube. And in a closed tube, we only have odd numbered harmonics, 1, 3, 5, 7, etc. In a tube that is open on both ends, we have even number or odd and even numbered harmonics. So because this is a closed tube, our second harmonic is going to be or the second frequency that resonates is going to be our third harmonic, is probably the least confusing way to say that. I know that can be kind of confusing, but just remember when we have a closed tube, we always just go 1, 3, 5, 7, etc. We don't specify a sound or a temperature, so we're going to assume at 20 degrees Celsius. I know at 20 degrees Celsius, the velocity of the sound wave is going to be 343 meters per second, and we are looking for the frequency. Now I can find the frequency using either my first or third harmonic. So let's use the frequency finding the first harmonic first. So the frequency for the first harmonic, and this is a closed tube, so the frequency is going to equal the number of the harmonic, which is my value for n, times the velocity divided by 4 times the length. So 1, which is my number of the harmonic, times 343 meters per second divided by 4 times 0.327 meters will give me a frequency of 262 hertz, which rounded to 3 significant figures will give me 262 hertz. Or I can use my third harmonic to find the frequency, and I'm going to follow the same formula. I just have to plug in the value for n for that harmonic, which is 3, because it's the third harmonic, n equals 3, and the length at which that harmonic frequency occurs. So when I plug those numbers into the equation and I use my speed of 343 meters per second and the length of my third harmonic, which is 0.982 meters, that will give me a frequency of 261.9 hertz, which rounded to 2 or 3 significant figures will give me 262 hertz. Now, one other thing I do want to point out to you guys is if you notice, the intermediate values we get are not exactly the same. They're close and they are the same to 3 significant figures, but they're off slightly. But that is why we use sig figs. We can only trust this value to 3 significant figures, which is 262 hertz. We can't extrapolate that out to 4 digits because we don't know with any confidence what those digits would be. So there's a good example of why significant figures are your friend. On to the next one. Problem 17. The 6 strings of a standard guitar are tuned to the following frequencies: 165, 220, 294, 392, 494, and 659 hertz. Find the lengths of the shortest open-ended organ pipes that would produce the same frequencies. So we're given the frequencies of each of these 6 guitar strings. We're not specifying a temperature, so we are going to assume 20 degrees Celsius. And I know my speed of a sound wave at 20 degrees Celsius is 343 meters per second. And we are looking for the length of an open pipe that would give me the same frequency. So I'm going to take my my standing wave formula for an open pipe, and we are looking for the fundamental frequencies for each of these pipes. So I know that my value for n is going to be 1, and I know that that can cancel out of the equation. So I'm going to have F equals velocity divided by 2 times the length. And when I solve for the length, I'm going to have the length is going to equal the velocity divided by 2f. So now I have to take this equation and plug in each of these 6 frequencies into that equation to get the length for each of those frequencies. So for our first frequency of 165 hertz, when I plug that into this formula, I am going to get a length of 104 meters. When I do the second frequency of 220 hertz, plug that into my formula, I'm going to have a length for the pipe of 0.78 meters. For my third frequency of 294 hertz, I plug that into my equation. That will give me a length of 0.583 meters. And for my fourth frequency of 392 hertz, I will have a length of 0.438 meters. For my fifth guitar string at 494 hertz, I will have a length of 0.347 meters. And for my final guitar string with a frequency of 659 hertz, I will have a length of 0.260 meters. Problem 18. An organ pipe is 112 centimeters long. What are the fundamental and first 3 audible overtones if the pipe is A, closed at one end? So our length of the organ pipe, 112 centimeters, is going to equal 1.12 meters. We are not specifying a temperature, so we'll use our default speed for the sound wave of 343 meters per second. And we are looking for the first or the fundamental harmonic and the next 3 harmonics. And because this this pipe is going to be closed at one end, we know that in a closed tube we only have odd numbered harmonics. So our first 4 harmonics are going to be numbers 1, 3, 5, and 7 because we only have the odd numbers in a closed tube. So I know that for my fundamental harmonic, that frequency is going to equal the number of the harmonic times the speed of the sound wave divided by 4 times the length of the pipe. And when I plug my known values into that equation, I'm going to get a fundamental frequency of 76.6 hertz. Now I know that my third harmonic is going to be 3 times my fundamental harmonic. So I take my fundamental harmonic and I multiply that by 3, and then I'm going to get 230 hertz, or 2.30 times 10 to the second hertz, to 3 significant figures. To find the frequency of the fifth harmonic, I simply take my fundamental harmonic, multiply that by 5, and that will give me 383 hertz. And for my 7th harmonic, I take my fundamental frequency and multiply that by 7. 7 times 76.6 hertz will give me a harmonic frequency of 536 hertz. Part B of problem 18 asks us to do the same procedure, but now for a pipe that is open on both ends. So I'm still looking for my fundamental harmonic and the next 3 harmonic frequencies in the series. But because this is an open pipe, I know that I have odd and even numbered harmonics. So I'm looking for the first, second, third, and fourth harmonic. I'm going to follow the same procedure as I did for the previous part. Of course, now I need to use my standing wave formula for an open pipe. And that is going to give me the number, the fundamental frequency, or I should say any of the frequencies, is going to be the number of the harmonic times the speed of the sound wave divided by 2 times the length of the pipe. So for my fundamental frequency, where my value for n is 1, I know it's going to equal 343 meters per second divided by 2 times 1.12 meters, and that will give me a fundamental frequency of 153 hertz. To find the frequency of the second harmonic, I simply take my fundamental frequency, multiply that by 2. So 2 times 153 hertz is going to be 306 hertz. For my third harmonic, I take my fundamental frequency and multiply that by 3. When I do that, I will have 459 hertz. And for my fourth harmonic, I take my fundamental frequency and multiply that by 4, which will give me 612 hertz. But just note that all of these harmonic frequencies are going to be multiples of my fundamental frequency. Problem 19. What resonant frequency would you expect from blowing across the top of an empty soda bottle that is 18 centimeters deep if you assumed it was a closed tube? Part B asks, how would you change that if it was 1/3 full of soda? So for the first part, I know that my length is 18 centimeters, so that will give me a length of the tube of 0.18 meters. Again, we're going to assume 20 degrees Celsius, which would give us a speed of the sound wave of 343 meters per second, and we are looking for our first harmonic or fundamental frequency. So because this is a closed tube, I will use my standing wave formula for a closed tube. So I know that the fundamental frequency is going to equal 1, which is my number of the frequency, or my number of the harmonic rather, times the speed of the sound wave divided by 4 times the length of the tube. I plug my values into that equation, and that will give me a fundamental frequency of 480 hertz. For the second part, if the bottle is 1/3 full, the length of my air column is then going to be reduced to 12 centimeters. If 1/3 of my soda bottle has soda in it, then there is 6 centimeters of soda in the bottle and 12 centimeters of air in the bottle. So now my length is going to be 0.12 meters. I follow the same procedure as I did for the first part using my standing wave formula. And when I plug my length of 0.12 meters into that formula, that will give me a fundamental frequency of 710 hertz. And lastly, problem number 20. If you were to build a pipe organ with open tube pipes spanning the range of human hearing from 20 hertz to 20 kilohertz, what would be the range of the lengths of pipes required? So I have 2 frequencies that I need to find the lengths for. My low end of the hearing range for humans of 20 hertz and a frequency at the high end of our hearing range of 20,000 hertz. Again, we're going to assume the velocity of the sound wave is 343 meters per second. And if we are building open tubed pipes, we are going to use our standing wave formula for open tubes. So I know that the frequency is going to equal, for my fundamental frequency, 1 times the velocity divided by 2 times the length. Solving that formula for length will give me length is going to equal velocity divided by 2 times the frequency. So for my 20 hertz pipe, I know it's going to be 343 meters per second divided by 2 times 20 hertz, and that will give me a length of 8.6 meters. For my 20 kilohertz pipe, I'm going to take my my wave speed of 343 meters per second, divide that by 2 times 20,000 hertz, and that will give me a length at 20 kilohertz of 8.6 times 10 to the minus 3rd meters, or 8.6 millimeters.